Have you ever watched a sci-fi movie and wondered if those futuristic biorobots could ever be real? You know, machines made of living tissue, blurring the line between life and technology. It sounds like something straight out of a Hollywood blockbuster, but what if I told you that scientists are already taking the first steps to make this a reality? Today, we're diving deep into the incredible world of biological robots, or biobots, to find out if we can truly build machines that are alive. So, what exactly is a biological robot? Forget the metal skeletons and circuit boards you're used to. A biobot is a machine powered by living cells, usually muscle cells, that are integrated with a non-biological scaffold. Think of it like this. You have a tiny, flexible skeleton, and instead of motors and gears, you have living muscle tissue that contracts and moves it. It's a fusion of biology and engineering, creating something entirely new. The idea isn't as new as you might think. For decades, scientists have dreamed of harnessing the power of biological systems for robotics. Why? Because nature is an incredible engineer. Our muscles are far more efficient, self-repairing, and adaptable than any man-made motor. Imagine a robot that could heal itself if it gets damaged, or one that could grow and adapt to its environment. That's the promise of biorobotics. So, how do you actually build one? The process is fascinating. It usually starts with a scaffold, which is like the robot's skeleton. This scaffold is often created using 3D printing technology, allowing for precise and complex designs. It needs to be flexible and, most importantly, biocompatible, meaning it won't harm the living cells that will be attached to it. Materials like soft polymers or hydrogels are often used. Once the skeleton is ready, the real magic begins. Scientists take living cells, typically muscle cells from animals like rats, or even engineered human cells, and seed them onto the scaffold. These cells are carefully cultured in a nutrient-rich environment, a bit like a tiny gym. Over time, these individual cells multiply, align, and fuse together to form functional muscle tissue that wraps around the scaffold. They naturally organize themselves into fibers, just like the muscles in our own bodies. But having muscle isn't enough. How do you get it to move? The muscles need a signal to contract. This is where things get even more interesting. One of the most common methods is using light. By genetically modifying the muscle cells to be light-sensitive, a technique called optogenetics, scientists can make them contract just by shining a pulse of light on them. Shine a light, the muscle contracts, and the biobot takes a step. By controlling the timing and location of these light pulses, they can make the biobot walk, swim, or even grip objects. It's like having a remote control for living tissue. We've seen some incredible examples of this in recent years. Researchers at the University of Illinois created tiny walking biobots, less than a centimeter long, powered by rat muscle cells. When they pulsed light, these little guys would walk across a petri dish. Another team at Harvard University built a biorobotic stingray that could swim through a liquid by using light-sensitive heart muscle cells from a rat. The cells were arranged to mimic the natural muscle structure of a real stingray, allowing it to navigate an obstacle course guided by light. It was an amazing demonstration of how biological design can inspire robotic function. More recently, scientists have even started using neurons, or brain cells, to create more complex control systems. They've managed to integrate clusters of neurons with the muscle tissue. These neurons can act as a simple brain for the biobot, creating rhythmic signals that drive the muscles without needing constant external stimulation from light. This is a huge step towards creating autonomous biobots that can move and react on their own. So, what's the point of all this? Are we just trying to build tiny Frankenstein's monsters in a lab? Not at all. The potential applications are revolutionary. In medicine, these biobots could one day be used for targeted drug delivery. Imagine a microscopic robot made of your own cells, swimming through your bloodstream to deliver medicine directly to a tumor, minimizing side effects. They could also be used as tiny surgeons, performing delicate operations inside the body that are impossible for human hands. Beyond medicine, biobots could be used as environmental sensors, swimming through water supplies to detect toxins or pollutants. Because they're biodegradable, they wouldn't leave behind any electronic waste. They could also help us understand fundamental principles of biology: how cells communicate, how tissues form, and how movement is generated. By building life, we can learn more about how life works. Of course, we're still in the very early days. The biobots we can build today are small, slow, and can only survive for a few weeks in carefully controlled lab conditions. There are huge challenges to overcome. How do we keep the cells alive and supplied with nutrients for longer periods? How do we scale them up to create larger, more powerful robots? And how do we control them with more complexity than just simple walking or swimming? And then there are the ethical questions. We are creating entities that exist in a gray area between machine and living organism. What rights, if any, should they have? As we get closer to creating more complex biobots, perhaps with more advanced neural networks, we'll need to have serious conversations about the implications of this technology. It's crucial that the science progresses hand in hand with ethical guidelines. So, is it possible to create a biological robot? The answer is a resounding yes. We're already doing it. Right now they are simple and microscopic, but the proof of concept is there. The fusion of living tissue and synthetic scaffolds is no longer science fiction. We're on the cusp of a new era in robotics, one where our machines are not just built, but grown. The journey from a simple, light-activated walker to a fully autonomous, self-healing biorobot will be long and full of challenges. But the potential to revolutionize medicine, environmental science, and our very understanding of life is undeniable. The future of robotics might not be made of metal and wires, but of muscle and sinew. What do you think about this technology? Is it exciting or a little unsettling? Let me know your thoughts in the comments below. And if you enjoyed this glimpse into the future of robotics, make sure to hit that like button and subscribe for more deep dives into the science that is shaping our world. Thanks for watching.